So this is Group 9's final project, the classroom noise level detector, where it uses two ADC inputs, one potentiometer and one microphone to essentially detect whether or not the current noise level in the surrounding area is acceptable. And that acceptable noise level can be set by the potentiometer, where it is shown as a percentage on the LCD screen. So for example, as we can see, as we increase the percentage of maximum acceptable volume, the general noise level changes. And so by increasing it, the more we talk at a normal talking voice, it becomes more acceptable along these LEDs, where red is too loud, and these are supposed to be yellow, but because even with adjusting to lower resistance resistors, the yellow LEDs that we were using did not show bright enough, so we changed them to blue. But as you can see, this is within acceptable noise for the 37%, and it's a talking level or a discussion level. And it does this by taking in the ADC input from the microphone and converting that to a value that we can interpret as the volume. And then that volume is then adjusted in code, as will be discussed later, and then converted into a 3-pin output that is then delivered to this decoder that will then convert it into an 8-pin output that will then power on these LEDs, where 0 is not here because it is naturally on as long as none of the other ones are on. And because we did not have NOT gates, we had to create NOT gates at the transistor level using 1.2K ohm resistors and some NPN transistors. And as such, these are grounded, which allows these outputs from the 18 mega are grounded, which allows it to be sent to the decoder, which then those outputs are then also inverted, because whenever they are sent out from this decoder, they are grounded. So we want them to power the LEDs, so we have to invert them again in order for them to power on the proper LEDs. So for example, if we start talking a little louder into the microphone, more of these lights light up, and if it reaches this red light, which indicates that you're too loud, as it showed there, it would be too loud. And that display changes and updates based on the volume compared to the acceptable range.
Okay, so looking at the code for our final project, first we're going to show the main function, which first calls the 328 dB initialization function. And then it sets the input and output for the data direction registers. So the output is set for port B, pin 3, 4, and 5, and input is enabled for port C, pin 0 and 1. So then we get into our actual main code, which is in the get mic values function. So if we go up to that function, we will first see that we initialize some variables. So we have a loop counter, a max noise level, and a volume percentage. So you'll see that all the following code is nested within a while loop, and this is basically just continuously reading in a new microphone value to check the outside volume. So first we read in our potentiometer value, and to read in from the potentiometer, we make sure that it's actually reading from the PC0 pin. So then we do our ADC underscore get assembly function and do the calculation to get this ADC value. And then we check whether the potentiometer value read in has actually changed from the last time it was checked. So this is what that if statement is doing, and if that potentiometer value has changed from last time, it'll get set to the input threshold, which is basically just the acceptable noise level that is set by the user using this potentiometer. So as you can see, the ADC value is actually divided by 6 and added to 170. And this is basically putting it in the same range that the microphone value is in. So the microphone value read in is usually within like a certain 100 to 200 range, a range of ADC value. And so this input threshold is being put within that range also. to be able to be easily compared to the mic value. So then the volume percent is calculated using this input threshold value. And next we read in the actual microphone value. So we set to read from the PC1 pin, which is where the microphone is hooked up. We once again do our ADC_get and do our calculations. And then this microphone value is gotten by taking the ADC value and subtracting the baseline, which is basically to allow the value to be centered around 1.1 volts, since it's a 3.3 volt microphone. So we reset port B every time, and then we get into our comparisons for the microphone value. So you will see for each if statement that a mic value is compared to an input threshold calculation. So for this calculation, you will see that each input threshold is divided by 10. So basically, this is calculating the increment for the certain input threshold. So for example, if the input threshold was read in to be 200, then the increment between each LED having to be turned on would be the value of 20. So looking at this else if statement, if the mic value is greater than the input threshold, then the first blue LED is turned on, and then for the next blue LED to be turned on, then it has to be the value 20 greater than the one before. So it would have to be between the range of 220 and 240 for the next blue to be turned on. And these calculations go for all these if statements. And within the if statement, you'll see that port B, 3 port B pins are set to a binary output from 0 to 7 to tell the decoder what LED to turn on. So finally, we will see our calculations for the LCD. So we will set our maximum noise level based on the LED that is turned on. And we also have a loop to actually print out the LCD. So first the volume percentage is calculated, and then the LCD function is called, and our variables are reset.
We've obtained our decoder value. We can now use that value to display on our LCD. And so we take our volume percentage based on the potentiometer value, and we make it a percentage of the maximum to base it off the sensitivity of what will make the mic go up a level in volume. And then now we go to our LCD, and we initialize all of our LCD commands, and we prepare a message. And so for this message, we take the percentage so that the teacher will know what level the potentiometer is at, so they can know what sensitivity level they have. And then setting the message for it as well, what noise level the class is on. We take that decoder value, and we essentially store the max decoder value that we got in a loop of about 5,000, I believe. 4,000. And so we take that highest value and we store it, and that's the max level that the students reached in that time. And so we take that and display what level they're at. So whether they're silent, whispering, being quiet, talking, discussing, they're loud or too loud. And that's associated with each light, with these 3 being green, these 2 being yellow, but this is connected into 2, so it's the 3. And instead of yellow, we're using blue, since the yellow lights, while we tried to use them originally, they were dim, and the blue lights worked much better for displaying brightly and easily to the user. And then this one displays the red light. And then we take that data and we set the number of lines to and the font size to 5x7 dots so that our message will always fit on the screen. And then we put that message onto the screen and clear the message for the next use. And then some other changes that we made was this in this assembly code. And so we initialized it like normal. And then when we did with the LCD write command, it's very similar to lab 3, but instead we had a few issues where we were taking in data, or like we had data stored in a certain variable, but that data was being altered whenever we were calling the LCD write command, specifically the port B values. And so what we did was we took the value from port B, stored it in register 18, added that to the value from register 16, which is 4, which is for the port 0, 1, and 2, but we were using 3, 4, and 5 to display the LEDs, and so we had to combine those values, and then return it to normal after. Then there was also another variable that we had to store in R19 and move it back at the end, because we were using R16 for something else. And then the LCD write data is the exact same with the port B situation, just moving it temporarily into R18, then transferring it back afterwards. So the LED will consistently stay on. And then for the analog to digital conversion, there were a couple variables that were also stored in register 16 and 17. And so we just stored them temporarily in register 22 and 23 and returned it back to normal afterwards. And so we were able to use good coding practices and reuse some of the code that we got from lab 3 and just repurpose it for our use.